Welcome to the video on electronegativity and bond polarity. Electronegativity is probably one of my favorite topics, so my students sort of laugh at me because this is one of my favorite words, terms, and I really emphasize this because it can tell us so much about a molecule, a bond, as well as its reactivity. And so if you go on any further to take more chemistry, or maybe one day you go back and take organic chemistry, this is where we start. So we talk about electronegativity. And if molecules have electronegative bonds, then they're more reactive. And so it really is sort of the basics behind all of that. So electronegativity, so what it is, it's a measure of an atom's attraction for electrons in a bond. Okay, and different atoms have different electronegativities, and basically it tells you how much a particular atom wants to hold on to electrons. And so I sort of think of this as a tug of war type situation, and I think I mentioned this in one of my lab videos, but basically if you have a bond, so this rope here is the bond, and you have two different atoms, okay, and we'll talk about what these could be, all right, but if one atom is more electronegative, it wants to pull harder on those two electrons that are in this bond, and so it's more electronegative. So in my way of thinking is that it wins the tug of war. Okay, so it's pulling those electrons. So the electrons, so if this is more electronegative atom, then the electrons are not equally shared in the bond, right? So they're going to be shifted towards the more electronegative atom. Okay, so if you look here, you don't have to really memorize values. You just have to know the trend. So the way I remember it, and the way my students I feel like remember it the best, is fluorine is the most electronegative. So if you move away from fluorine to the left, or you move down away from it on the periodic table, then you are becoming less electronegative. Okay, and so we can put numbers on this. We can look at differences. So if you look at, carbon versus fluorine, okay, so you have an electronegativity difference of about 1.5. Okay, and that's considered large in the scheme of electronegativity. Okay, if you have electronegativities of two bonded atoms that are the same atom, so let's look at that first. So if we have a carbon bonded to a carbon, well, the electronegativity value of carbon is 2.5 and of carbon is 2.5, so there's no difference. So 2.5 minus 2.5 is 0. Okay, and we consider this to be a non-polar bond. Okay, so electronegativity and polarity go together, okay? Go hand in hand, basically. All right. So here we have 0 difference. So our electronegativity difference is 0. And so we consider this to be non-polar. All right. Here we have a carbon and a hydrogen. So if you look back at that table, it's about 2.5 to 2.1. So 2.5 minus 2.1 equals 0.4. This is so small of a difference that we consider it to be negligible. It's ignored. And so we still consider a CH bond to be non-polar, meaning there's not a big difference between the electronegativity. So what this means is that these guys play fair, right? They are sharing their electrons equally. So the electrons are pretty much smack dab right there in the middle, shared between both. So neither one is pulling harder. They're shared equally and right there in the middle. Okay, so this is called non-polar, a non-polar bond. might already have guessed it, but we have nonpolar bonds and we have polar bonds. Okay, if you have two atoms with a difference in electronegativity, then these are considered to be polar bonds. Okay, and we call them polar covalent bonds. Okay, and so if you look at a carbon-oxygen bond, okay, so if you look back, I believe it's the values 2.5 and 3.5. Those are our electronegativity values. Okay, so they have a difference of 1 in electronegativity, and that is considered to be polar. All right, so a carbon, so here's carbon, green, the green, and here is oxygen. Okay, so if oxygen is more electronegative, it's closer to fluorine, then the electrons are not shared equally. So we have a tug-of-war situation going on, and oxygen wins. So the electrons in the bond are shifted towards the oxygen. Okay, electrons are negative, so that puts a partial, that's what this is right here, this little delta here means partial. Okay, it's not a full charge, okay, but it's a partial negative charge on the oxygen. And so you'll see it written, so put a partial negative, which leaves this partial positive because it was losing the tug of war of electrons. So the electrons are not as close to it, and leaving it more positive since electrons are negative. Okay, this is called a dipole when this happens. So if you have a polar bond, it has a dipole, and that just means it has a difference in electronegativity, that it is a polar bond, and there is a separation of charge. Okay, and we see that. We have a partial positive and a partial negative. Okay, therefore, there is an unequal sharing of electrons because of the difference in electronegativity, and therefore these are called polar covalent bonds. All right, so if you have a difference in electronegativity, then in the bond it's called a polar covalent bond. Okay, this whole series of videos, can't remember if I mentioned it or not, but we're talking about covalent compounds. Okay, so that means that we have nonmetals bonded to other nonmetals. All right, so if you have a difference in electronegativity in the bond, you have charge separation, you have a dipole, then this is called polar covalent bond. All right, if, we're going to go back for a second, if you have zero difference or something very small, okay, and we're going to put kind of values on this in a second, okay, then this is called a nonpolar bond. So we actually call this a nonpolar covalent bond. Okay, so what we're learning here is that all through this series of videos, we've learned that we have ionic compounds and covalent compounds, or ionic bonds and covalent bonds. That's our two types, main classes of bonding. Okay, ionic was between metals and nonmetals, and then these last few videos have been on covalent molecules, and that means we have nonmetals bonded to each other. Okay, but within, so you sort of have within covalent bonds, you have two subclasses, if you want to think of it that way. You have nonpolar covalent bonds, okay, and this is what we just went over, and this is when the bond type is nonpolar. So that means that there is equal shared electrons, equal sharing between the atoms, and the electronegativity difference is either 0 or very small, so less than 0.5, so anywhere from 0 to 0.4. Okay, so this was like our CH bond, had a difference of 0.4, so we still consider it nonpolar. Okay, polar covalent, this is when we have a difference in electronegativity anywhere between 0.5 and 1.9 units. Okay, this is polar covalent, and this means our electrons, just like our carbon and our oxygen example, are not shared equally. They are pulled towards the more electronegative atom, and that creates a dipole. Okay, ionic compounds, these are actually have the largest electronegativity difference. So think about it. As you move further and further away, the electronegativity differences get larger and larger. Okay, so ionic compounds, they have an electronegativity difference of greater than 1.9. Okay, remember, but ionic compounds are metals bonded to nonmetals. Okay, and this is why those electrons are transferred from the less electronegative element to the more electronegative element. Okay, but they're ionic because they have a large separation. So these have the largest separation of electronegativity values, the biggest difference in electronegativity values. Okay, but the main idea from this lecture is looking at covalent compounds. That's what this series of videos is about, and knowing whether it's nonpolar or a polar covalent bond. All right, I hope this helps. Thanks.